Or guess.
Yeah, all right. Hey everyone. So today I'm going to talk about a paper which offers a new way to compute a gradient. This is going to be related mostly to machine learning and gradient descent and how we train our models. So there's going to be a bit of math. And let us start with a recap of gradient descent. So in general, gradient descent is a technique for optimization. It allows us to minimize a function using its gradient. So this method relies on computing the gradients to make updates. In machine learning, we are trying to minimize the error function, the loss function. And by minimizing it, we are trying to find the weights of a model which correspond to the smallest loss. So this is a minimization problem. And we are solving it usually using gradient descent or some modifications which try to optimize it, like, Adam, mental approaches, and so on. But still, all these approaches required you to compute the gradient. And so far, we've been mostly using backpropagation for it. It's a quite good technique. It allows us to compute the exact gradient fairly quickly and use it to train our models. However, backpropagation is not the only thing you can use to compute a gradient. So about half a year ago, I was giving a talk about a paper presenting forward gradient. It's another approach for computing gradients. Unlike backpropagation, it does not allow us to compute the exact gradient, but it allows us to estimate it somewhat randomly. And this kind of random gradient can be used to train the models. So here you see its definition. It relies on, this is the expression for forward gradient. You can see the true gradient here and some vector v. V is a random vector. Okay, let's see. So a few words about forward mode and backpropagation. So these two techniques rely on automatic differentiation, and this is a technique for computing kind of Jacobian vector products and these kind of things. There exist two different modes of AD. Reverse mode is used for backpropagation. As I said, it allows us to compute the exact gradient, and we use it a lot. Forward gradient relies on forward mode, automatic differentiation. It is slightly different. It allows us to compute Jacobian vector product. It is not exactly the gradient we're looking for, but still, this mode of ID is typically faster. So if we find a way to use it to train our models, we can expect that it will do it faster and maybe sometimes even better than if we are using true gradient. And so in this paper, they showed these results after comparing the forward gradient and backpropagation. And what these results show is that forward gradient is typically faster. And moreover, it is also better at actually minimizing the loss function. So the blue lines here are the forward gradient. Maybe I have a pointer, one moment. Yeah, and for example, if we look at this picture, we see that forward gradient first minimizes the loss better, and second, it is doing it faster than the backpropagation. So this is quite promising, this is quite interesting, but there are a few issues with this paper. First, it seems like nobody was able to actually reproduce the results obtained in the paper. I was trying to do that, and I got kind of reverse results. Forward mode was twice slower than backpropagation, and it was also less accurate. And that's one problem. Another problem is that the forward gradient we are using relies on us making guesses about its direction, the direction of the gradient. And with the increasing number of dimensions, with the increasing number of guesses we are making, the cosine similarity of our guessed gradient and the true gradient are approaching zero. And for us, it means that if we try to use it in neural networks, to train neural networks, it will probably be quite inefficient, as the gradient we are using is almost orthogonal to the true gradient, and we do not update our weights in the right direction. Okay.
Sorry, is that a theoretical result, Pavel, that it's orthogonal, or is that just what you found or what others have found empirically?
Curse of dimensionals. Anything will be orthogonal. Any two random vectors are orthogonal.
Right. Yeah.
Yeah, all right. So what can we do about it? I can do nothing, but some people in MIT and Berkeley managed to find a few methods how to make the guesses of our gradient better, so that the cosine similarity between the estimated gradient and the true gradient gets better and is not as bad for training neural networks. Okay.
So basically the goal is not to do just random guesses. What is the forward gradient, forward propagation? Forward propagation gives you gradient along a direction. So you have to pick a direction. The V is the direction along which you want a value of gradient. And once you chose a direction, dimensional space, gradient becomes scalar value. It's like just along this direction. And if you choose your directions incorrectly, then you are moving. But how much you will be moving will determine how incorrect you are. Because if you're orthogonal, you will not be moving, right? It's like the derivative will be zero. But if you're aligned, then you're making a maximal step. If you're off, slightly off, you're going slower, but in the wrong direction. So if you're at least in the cone, then this random movement will get you closer to the goal versus, you know, staying around. And that's what they're trying to do here. How do we guess this cone or direction along the true gradient without calculating the true gradient?
Yeah, that's correct. So let's so this paper presents a few methods to, you know, make a better guess, and they show a lot of results. Personally, I think the most interesting thing about this paper is the methods, so maybe they'll pay more attention to it. Don't be afraid to ask questions if you manage to follow it. So let's start reviewing what they did. They introduce a notation. They consider a simple MLP with k layers and neurons at each layer. And so Wi are the weights on the ith layer. Xi is the incoming activations. Si is a product of weights and incoming activations, which we call pre-activations. And finally, xi plus 1 is the ReLU of pre-activations. So far, so good. Okay, so we want to know the gradient, and the gradient we want to know is dl by dw. That's the gradient of the loss function with respect to weights. On the ith level, the weights have n squared elements, and so we want to find a way to make guesses on the directional in this gradient such that we are not too far away from the true gradient. And one way to do it is to try to reduce the dimensionality of your guesses. So the less dimensions you have, you can expect the more cosine similarity you will get for your true gradient, for your estimated gradient and the true gradient. Okay, so what can be done here? They start with, unfolding this expression for gradients. So the gradient of loss with respect to weights can be unfolded as this, as pre-activations, derivative with respect to pre-activations, and the derivative of pre-activations with respect to the weights. And this expression can be actually computed, and we get X transposed. So what do we have here? We started with this. It has n squared dimensions, and we are ending with this expression. And in this expression, this element, this term is known, and this element has n elements. So we effectively reduced our problem from making n squared guesses to making only n guesses. That's quite good result. But it is not that novel. Some people before did that. So what do they do next? This is clear so far.
Yeah, this is an outer product formulation, right? And because your DL by DW, what is sub I? Layer?
Yeah, I is a layer.
So it's a matrix, and you represent this matrix, not represent it. That's how it's computed as an outer product at the rightmost part of this expression.
Mm-hmm.
Activation post times your adjoint, I guess. That's what it.
Mm-hmm. Okay, let's move next. So we ended up with this expression, right? We know X transpose. We need to do something with the other derivative. Let's expand it further. So this derivative can be expanded this way. So this is the activations for the next layer. And this is the derivative of activations with respect to pre-activations. And this is actually a fairly simple expression. It's derivative of real U with respect to pre-activations. And it is actually a fairly simple matrix. It's a diagonal matrix, which is populated with zeros and ones. So when pre-activation is less than 0, the derivative is 0. When the pre-activation is greater, the derivative is 1. Fairly simple. What did we achieve here? So we had this, it has n components, and we ended with this. It also has n components, and this diagonal matrix. Since this matrix is sparse, we can expect that if we kind of uncouple the first term into this form, we can again make n guesses on this. But when we multiply it by this, we are actually effectively reducing the number of guesses we make because this matrix is sparse. And that's another improvement. We managed to make the dimensions of our problem small. That's okay.
But you don't know S, right?
Like, they're just saying that you can compute it during the forward pass release, like, because it's a value, so the derivative is.
Oh, you know the zeros.
Yeah. So
Yeah, we do.
Yeah, this is about the outer product position. Yeah. That's why Barak sent it.
Okay.
Yeah, all right. And the last thing they try to expand is this. Sorry, is this term. What are they doing with it? So they expand it again, and they get this. And so what do we have here? Again, we had n elements, n guesses. And in the end, we also have to make n guesses, and we have this matrix. So this matrix is kind of not very clear what it is. it is initialized with random variables and that kind of things. But still, we know that typically the weights in neural networks represent a low rank matrix. So,
So the weights don't have to be, especially at initialization. It could be full, because you're visualizing from a noise distribution, it actually will be full rank. It's the gradients, they are not, but the matrix.
Because the weights are a product of low rank gradients, they're, I'm sorry, I'm some.
They usually start as full rank though.
Yeah,
Exactly, that's what we're saying.
No, and then they keep being full
Yeah.
rank, like how can they not be? full
It would
rank?
be weird for them to lose.
Well,
rank
it's
and
possible,
It's possible,
but
Yeah.
it's possible, but
I haven't seen any theory actually showing this. People have found it empirically in some architectures, but it's theory.
they have shown that low rank, like if you initialize with a low rank matrix, it trains poorly. As a little tangent.
transported.
Anyway,
I
assuming.
don't know, maybe
Yeah, let's
maybe when
let's
we train our
assume-
model, it will become less ranked.
Oh,
if
it's
you
trained.
train it.
Not necessarily, because it's this matrix, the initial matrix. And I mean, it's not exactly, but because there is a recursion component, but this plus collection of all of your gradients. And collection of all of your gradients may tend to be full rank as well. So full rank plus full rank equals to the rank.
Well, I don't know. Let's assume it is low rank,
Mhm.
because if it is not, then well, it's
Yeah,
not this
that's
big of a deal. Anyway, so they reason that since this WT is low rank, the guesses we make on the first term and guesses will effectively become less guesses, and again less dimensions and better cosine similarity. Let's sum up what did they do. So they expanded the gradient, and they did it in 3 steps. They start with this, then this, then this. So this term allows us to go from n squared to n guesses. This term allows us to go from n guesses to, again, n guesses, but it's probably less than n. And the same applies to this. So we had n squared guesses in the beginning, and we have to make only n guesses or less in the end. That should improve our cosine similarity, and that should improve the convergence of a gradient descent, which uses this method to estimate the gradient. Okay. Let's move on.
Okay.
Let's see the results. So they call this method W transposed. And on this figure, they are showing the results of this method and comparisons of it with other methods. So far, I introduced WT. You are familiar with backpropagation, black line on top, and you're familiar with directional descent. It's actually just forward gradient without any attempts to improve, the similarity. And we have a lot of models in between of them. And what we can get from this figure now is that doing all these steps, reducing the dimensionality of our problem, drastically improved the cosine similarity of the estimated gradient. So the truly random gradient has similarity.
Allow me to interrupt. Cosine similarity between what and what? The true gradient, the
Between the
background.
true gradient.
Okay, so
Between the true
background-
gradient and the estimated gradient. In case of
Okay.
backpropagation, estimated is true. So cosine similarity is 1. Yeah. truly random gradient has a terrible cosine similarity. And these methods are showing, well, still fairly low cosine similarity, but it is way better than what used to be, what the truly random gradient was offering.
Well, why is it significant? Because we're doing stochastic gradient descent. The gradient that backprop computes is incorrect anyways with respect to the entire data set. It's just an approximation. Why do we strive or need to strive to be as good as already something bad? The gradient only matters as long as it's in the correct general direction. Because if you do batch optimization, entire data set, it will be different. And the error surface is different. And if you're doing infinite data optimization, the error surface may yet still be different. So what is the motivation? Do they give a motivation? Why do we want to be why is it required to achieve the minimum to be as good as backprop, as true gradient that is already wrong because it's computed at the min batch? Or stochastic one of those.
40% faster, right? And it converges ostensibly. That's like the paper that Pavel showed at the start is that supposedly is faster for convergence and stuff.
No, if your gradient is correct, it will be faster for convergence. That's what I mean. Why do you want to be like? You don't have to be exactly as backprop in order to be still correct and fast. Forward descent faster because you compute less. It's like it's actually the factor k in front of them. It's smaller. You also compute as
well, we're going to see on the next slide that the cosine similarity seems to affect the speed of convergence.
Okay.
So
it correlates with performance.
Mm-hmm.
Okay, thanks.
I have another question actually. Why do we need backpropagation at all? Alternatives to backpropagation that do not, use the reverse mode. I've heard of biologically plausible training mechanisms like that's topic some people are researching, but I'm not quite sure why do we need it.
Long and short of
Apart
what
from,
I've seen is that they're not as stable, and they don't the kinds of networks that a lot of the biologically so equilibrium propagation and stuff, like they just don't which is a more biologically plausible version of backprop, doesn't converge as stably as backprop does. Things like Hebbian learning, like the networks that they work on are just very different from the ones that are in application. So it's just a popularity contest, I think.
I heard of a recent one that they used to train spiking neural networks quite efficiently. I forgot the name. But there is something that is a winner right now, like some algorithm. But I don't think it is fully biologically plausible. And I'm not sure. I'm fine with backprop. Gradient makes total sense. But what I'm saying is when you do SGD, your gradient is just an approximation itself. So I don't know.
Yeah, I guess we can differentiate different estimations of the gradient by how well they minimize the loss function.
Maybe the argument, right, is that SGD is already an estimation, but then if you do standard forward directional descent, it's a worse approximation or a bad approximation versus not a better approximation of a decent approximation. Right?
Yeah, so if we have a proof or if we know that backprop or AD reverse mode is a good approximation to the true whatever, then yes, we need to at least strive for the picture approximately. Okay. I'm eager to see the next slide. Oh, no, not this one.
Oh, yeah.
Okay.
So, yeah, not this slide. So you see there are, apart from W transpose, there are a few other models in this region. So what these models are? One of them is partial backpropagation. It is kind of W transposed, but with a slight difference. Something bad happened to the formatting. Okay. So partial backpropagation also makes guesses like W transposed. But instead of doing all these steps, instead of doing all of this, they are actually just make one guess on some downstream layers and then backpropagate this guess to the upper layers and make the guess on the gradient this way. Is it clear or not? Well, to be fair, it's not that important.
Partial backpropagation. Partial. So they are using backpropagation.
In another method, yeah. So they're comparing, I think, 4 methods in total, plus the backpropagation and the forward gradient.
Oh.
So this partial backpropagation can actually be, you know, just backpropagation in the limit if your L, the downstream layers are the last layer. Or it can be quite close to WT if your L is 1. So you're making assumptions on the next layer.
Yeah, assuming what you've done, Brad, was like keeping activations.
Yeah.
And only dealing with deltas here, so it could be exact as well. Yeah, okay.
Another method is activation perturbation. I think this one was established before. It's actually the first step of WT, which uses this. It reduces the number of dimensions from n squared to n by making guesses in the pre-activation space. Okay. And the last method, it's kind of complicated, but also one of the more interesting, I think. So it's also kind of WT, but instead of doing the last step the way WT does it by, you know, expanding the activations of I don't remember what and getting the weights from the next layer, multiplying and expecting that it is a good step. Anyway, here they do it differently. They try to make assumptions on the activations from the next layer by putting those assumptions in a space which is formed by activations from the previous iterations. Is it okay? Did anyone understand anything?
Activation mixing. Well,
It's kind of small, but yeah, the reason that this
oh yeah, that's like so for previous iteration. So it's like what's the method? Arrival method was called
Power SGD.
RSGD.
Yeah, they do something similar.
Yeah. It's okay. There's some kind of like a running average with step 1 or something like that. Yeah, some inertia. Okay.
Yeah, power
So
SGD
maybe.
actually uses the previous eigenvectors for
Okay.
And that one works better.
I think WT is the best, but they are comparable.
I just have to laugh because it's funny, they have a section named intuition and then like 80% of that section is just equations. It doesn't seem.
No, well,
No, I get it, it's just, it's
Yeah,
funny
yeah.
to see.
it's just they mean
Yeah,
this.
that's nice.
It's
Yeah,
not
yeah.
like it's not proof for it. Okay, but if you go to that plot of the comparison plot with backprop, yeah, the blue, this one layer downstream is higher than W transpose, right?
I think that's yeah, the only time it is better.
Okay, so W transpose is,
And plus, it's quite close to W transpose.
yes, yes.
So yeah, back propagation has a perfect cosine similarity with true gradient. Forward gradient has
No, okay, I object to this words. Back propagation has perfect cosine similarity with itself. Let's just say it. We don't know the true gradient. We know true gradient on that sample with that sample, which is back propagation. It computes true gradient.
I don't think in this paper they're talking about SGP at all. I mean, they use an MLP, so they're probably doing full batch or full. data set.
No, it's one single sample that they can see.
Is it a single sample?
Yeah, single sample.
even worse.
Yeah, X of one.
well.
Yeah, with itself, the cosine similarity will be one. Or no.
Yeah. Let's maybe call the true gradient as the gradient computed for the mini batch or the stochastic gradient, these kind of things. So that back propagation is actually the true gradient.
Back propagation is the true gradient here, I assume, yeah.
Yeah. Well, let's define it this way.
Numerical precision of the machine.
Yeah. So anyway, back propagation has a good cosine similarity. Forward gradient has a bad one. It is this number. And you see that the rest of the methods they are testing are showing much better cosine similarity than the forward gradient.
But still very
And-
bad.
Well, it is bad, but they actually showing that it is enough for a good kind of training.
What is one
And
step?
this- It's the effectiveness of minimizing the loss function per step with respect to back propagation. So
if
suppose if
do you mean like if back propagation drives loss 1 unit down, then
Yeah. the others,
the 3 orders of magnitude slower, basically. Only, 1,000 unit, 1,000ths of a unit down, or 2.7 thousandths of a unit down. So very inefficient.
true, but it is also 1,000 times faster than the forward gradient. So I think that's a success. Is in this.
So it has to make 1,000 more steps.
I suppose. We may hope that those steps will be, computed faster. But I guess 1,000 times slower is still a bad result.
Mhm.
But
Did
it's
they
an
try-
improvement.
Did they try training with this W transpose?
Yeah, it's finally this slide I was going to show. So they're showing the evolution of train accuracy and test accuracy over the with the increase of the number of components the gradient tries to estimate. So I don't know, are we interested in train accuracy? So it appears that on MNIST, all those methods are doing well, but on more difficult datasets, these forward gradient based approaches are becoming less efficient than the back propagation on the test accuracy, but when we on the train accuracy. But when we see the test accuracy, we see that it is not, well, it is, these methods are not as good as back propagation, but they are not as bad as they were on training. So even though training is not that good, the generalizability is not as bad as we could have expected.
This is a difficult, I'm having trouble understanding this plot. Train accuracy, test accuracy. So backprop trains well, but doesn't generalize.
No, back propagation generalizes, and it's kind of the best technique on this slide.
Well, unclear. For Sci-Par 10, no, like all of them, backpropagation does not generalize better than any other method. Mhm. Well, we don't have error bars here, so I assume they overlap with the next method. So I assume they don't, they're not better than the next method. The black line and the turquoise look the same to me. And that is to my point of why is it good to consider backpropagation as the gold standard, because it accelerates an approximation. That's one way to interpret this fact. The difference in the test error with the turquoise is minimal in all of them. So
What is turquoise? Is it the last model?
it's the teal blue, like whatever that color is called. Yeah, turquoise is the most the closest to it. It's not the bottom blue, it's the top blue. English is
Okay.
very good with blue. One word for everything. The sky blue. Okay, how about that? Do you know what I'm talking about? Right? This line.
Which
See this
line?
Yeah, the top line.
Yeah, okay.
This line is almost as good as backpropagation or as good as backpropagation.
Oh, I don't see your pointer, I think.
Oh, you don't.
Mhm.
Then I can tell you. But what I mean is, it is called W transpose. Okay, I found the legend. The W transpose in test accuracy is as good as backprop oracle. That's my claim. My claim
On
is
MNIST, I think. But not on MNIST, but not on the
Everywhere.
other.
everywhere on this 4 plots. All right, if they done proper statistical testing where there would be a variance on them, they would be
Yeah.
indistinguishable. That's my hypothesis, unless proven otherwise. And that means you don't have to be as good as by prop, but maybe you, at least on this plot to generalize. What about the others?
Well, I
The-
think they all kind of fall in the same category, which is not backpropagation. So there is backpropagation and there are other models.
No. Do they have
Backpropagation.
other experiments? That's what I mean. This figure, like I think, is finally clear, but the message is unclear.
Yeah.
The message is like,
Where did this get published, Pavel, do you know?
Last year, I think.
where
January, maybe.
I clear.
Don't remember.
It's crazy.
It's it looks like I clear the formatting.
Well, I think the message of this figure was supposed to be that these methods can be used to train the models. And
No,
they
but
are not
they're
as good as
saying-
backpropagation, but they still work.
No, but they're saying the gap between our methods and backcrop training accuracy. Yeah, training accuracy increases, but testing, it doesn't affect testing accuracy, which is interesting. So another interpretation is this is a regularizer. Just because backprop is approximating incorrect thing. Anyway, it's not approximating, but computing. Adding a little randomness regularizes the model. Generalization is doesn't suffer.
Yeah.
But we can make it better, of course, to be above backprop on test accuracy, while still being lower on train.
I think all the models are worse than backpropagation on test accuracy. Backpropagation is black line and it seems like it's on top.
I don't see the error bars. It's yeah. This is a meaningful plot. Meaningless, because there are no error bars. I assume that the error bars are wide enough such that there is no difference between the 2 top methods. If you actually look en masse. some kind of statistical comparison. Comparing 2 points is not informative.
Mhm. Well, I don't know. Let's agree that these methods are working. They can they can be used to minimize the
They're
loss
doing
function.
something. But was there a theoretical proof in this paper that they will not be as good in what I don't know? But they will not be as good as something.
There was estimation based on cosine similarity. That since these methods have less cosine similarity with the true gradient, they will be worse than backpropagation.
But they're not showing that. Okay. In
They're
train,
showing it here, I think.
well, okay, it's not a proof. It's just a guess.
Well, yeah, it just shows the average cosine similarity returned by these techniques, methods.
But we care about test accuracy. We don't care about train accuracy. Okay, backprobe over feeds, so what? Test accuracy is important, and they will never be as good. How? I don't see it. They're already as good. Okay, anyway, Pavel, this is not against you. This is just trying to understand what's on the plot here. But yeah. Do you have more slides? We have 10 minutes.
Yeah, we do. Let me check. Yeah, not that many. Okay, so they established that these methods have good cosine similarity and they can be used to train models. Next, they kind of delve into details. First, they find that this WT gradient is actually biased. So that explains one of the why it may be worse than backpropagation. So in this figure, we see that W transpose, light blue, and one layer downstream are reaching a plateau which is not one. They're reaching the plateau of cosine similarity. Yeah. And it is not perfect, which means that the gradients they predict are a little biased. This doesn't happen to activation perturbation, by the way, but it also seems like it is slower to make a good at making good estimations. Then they are trying to find out how forward gradient, here it is called directional descent, will behave if they try to improve its cosine similarity to the cosine similarity of the methods and do nothing else and check how well it is performing. And they see that then forward gradient has a better cosine similarity, not the 10 to the power of minus 4. It used to have about 10 to the power to the minus of 2. Forward gradient actually becomes quite good and better than the proposed models. So I think it proves that forward gradient can be good. Its main issue is that it is given bad cosine similarity. But then its cosine similarity reaches, 10 to the power of minus 2. It seems like it is
This is
already
a strange
good.
statement. You're saying
Okay.
if this goes into the right direction, it can be good. But the purpose of forward gradient is to find the right direction, not to go like, yeah, if we know where to go, we can be good. So
They're just trying to estimate the influence of cosine similarity. So they have two things to consider about their methods: cosine similarity and the bias. They are trying to find out which of these things affects the training more.
How do they match cosine similarity? What do they
I
mean
don't
by
exactly
match?
remember, but they are doing it kind of artificially. So the forward gradient gives you a gradient, and you can do back propagation to find the true gradient. Then you can modify your forward gradient in a way that its cosine similarity matches the cosine similarity of their methods.
So that means
So it's
you're
kind of
getting
artificial
into the
approach.
cone, into the same cone, like the cosine
Yeah,
similarity.
yeah.
Yeah,
Mhm.
so,
And we see that forward
I
gradient,
mean-
when its cosine similarity is improved, is
Yeah.
doing better.
what else do they expect?
So yeah, it's reviewers have rejected us for much less. It's silly. It's-
Yeah, but I mean, it's kind of obvious, if you are going in the correct direction, you will get to the correct place. I must be missing something.
Well, there are degrees of correctness of your direction. It can be perfectly correct, it can be orthogonal. Most of the estimations are falling somewhere between. And we know that with the increase of guesses, this, the cosine similarity between the predicted gradient and the true gradient gets to 0.
Yeah, forward, because of its constrained nature that it doesn't need that much to operate and can be computed while you're computing your function practically at the same cost, is attractive in some applications that I'm interested in, but only if it works. Okay, next slide.
Yeah. So they are analyzing how the other optimization techniques like momentum and that kind of stuff, Adam, are affecting these methods. And they see that there is a strange behavior here. So these two lines, this one and this one, are a comparison of gradient of forward gradient, the darker blue, and the W transpose. And they see that when they add momentum to the equation, the forward gradient looks better. This line, it is higher than this line. But then whereas there is no gradient, they get this. So there is no difference between them.
No momentum.
Yeah, without momentum, they look the same. When the
And
cosine
matched.
similarity is matched, yeah.
What is matched? Is this
Matched, it means the matched cosine similarity between W transpose and the output of forward gradient.
Mhm.
So kind of what happened here.
Mhm.
Okay, yeah, so these results show that there is a strange interaction between momentum and the bias of their methods. And finally, one last result is this. So they were training those neural networks for some time, and they found out that at some point, at some epoch, the cosine similarity of their gradients are actually getting better. So like it was going like here, suddenly it jumps here. Actually, I was going to show this one. So this is cosine similarity, and we see that with the improving cosine similarity, the training accuracy also gets better. They're not quite sure why it is happening, but they reason that probably during training, the ranks of weights are getting lower. Like you remember, there were multiplication by WT. So they assume that the rank of this thing is getting lower, and this in turn makes the number of guesses they make less. And this in turn makes the cosine similarity better and the training accuracy better.
So I disagree with that. I think, so we've seen the same thing in the rank of gradients changing during training, and that makes more sense because so for classification problems, for example, you'd expect as you get more and more samples correct, less are contributing to the gradient, you would expect sparsity to appear. As especially if your loss function is like activating less for particular samples or particular parts of the feature space or something, you're delineating things more. I think that makes a lot more sense than just saying the weights become low rank, artificially for no reason.
Well, in their case, the lower rank means better guesses. Maybe it doesn't apply to backpropagation, but to their case.
No, what Brad is reacting to is the weights become low rank.
I don't think that's right.
Yeah, we haven't seen it ever. We've read in literatures people and we'll look specifically for that, or all kinds of models, transformers and stuff. No.
Yeah, I don't see why it would happen anyway. Like I would get why the gradients, because the loss function, potentially sparsify as you get better guesses in your for a classification problem, for example. But I think this is I don't agree. And they don't
So
show
we're
any
kind of
hypothesis, so I could just disagree with that.
Yeah, without evidence, without evidence.
Yeah.
Anyway,
we're kind of out of time, but there is one last result related to this, to the rank. Maybe Brad will make sense of it. So this second row, it is showing different results. It shows us how, oh my God, I don't know what it is. So they did something with gradient, decomposed it using singular value decomposition, and tried to play with the singular values. They reason that it equals to change of the rank of matrix. But I kind of forget what this matrix is.
rank of the gradient, right?
Yeah, but gradient is a vector. What does it mean?
Gradient's not a vector.
Yeah, gradient is a matrix that you apply to your weight. But they're applying out
okay,
product,
yeah.
using only one sample, so fully stochastic, right?
What are you talking about?
They are computing their gradient on a single sample, single input, not a batch.
I am not sure. I think
Never mind. Yeah,
they
let's
were-
because we're out of
So-
time. I don't want to. But I'll dig
Mhm.
into the paper because I think this is there's something interesting along this line.
So here they say they are using SGD, but I'm not sure if it's SGD everywhere else. Well, okay, I think that's all.
Yeah, thank you. That's very interesting, and the slides have a lot of detail. Thanks everyone. We'll go according to schedule, which only Joanne knows. What next?
Let's see. Let me check the calendar.
Yeah.